Welcome back to the sixth episode of our BIO259 recap podcast. Today, we're diving into the structures that literally help hold your body together: connective tissues and cartilage. And trust me, this is way more exciting than it sounds. Let's get at it.
Oh yeah, Eric, this is where things get super interesting. I love teaching about connective tissues because these are the unsung heroes of our anatomy. I mean, without them, we'd fall apart.
Okay, let's start with connective tissues. Specifically, the differences between dense regular and dense irregular connective tissues. Let's break it down for everyone.
All right, so dense regular connective tissue, picture this. It's like a neatly bundled stack of ropes with all the collagen fibers aligned in the same direction. This makes it incredibly strong, but only in that direction. You'll find it in places like tendons, which connect muscle to bone, or ligaments, which connect bone to bone. These structures can withstand pulling forces, but only along the length of the fibers.
And then there's dense irregular connective tissue. It's not so, well, regular, right?
Exactly. It's like a crisscross jumble of collagen fibers. Think of it as a quilt where the stitching goes in all sorts of directions. That means it's strong not just in one direction, but in every direction. You'll find this in your dermis, under the top layer of your skin. It's why your skin can handle being stretched and twisted without tearing. Oh, and it's also in joint capsules and even the outer layers of our bones.
That's amazing. It's like our bodies are engineered for flexibility and durability at the same time. Now, pivoting a bit, let's talk about cartilage. There are three types we need to know: hyaline, elastic, and fibrocartilage. Where do we even start?
Oh, let's start with hyaline. Hyaline cartilage is like the smooth, glassy surface you'll find on the ends of bones at your joints. Its job is to reduce friction and allow smooth movement. It's also in your nose and the cartilage part of your ribs. By the way, this is the most common type of cartilage in your body.
Okay, smooth as glass. Got it. What about elastic cartilage?
Elastic cartilage is so cool. It's all about flexibility. You'll find it in places that need to snap back into shape, like your external ear and the epiglottis. The epiglottis is that flap of tissue that keeps food from going down your windpipe when you're eating. Like, imagine choking on food because your airway wasn't properly closed off.
Yeah, I'd like to avoid that visual. Okay, last one. Fibrocartilage, right?
Yep, fibrocartilage is built for heavy-duty support. It's tough and can resist compressive forces like a champ. You'll find it in areas like the intervertebral discs in your spine, your meniscus in the knee, and even at the pubic symphysis. It's basically a shock absorber, preventing bones from grinding together.
So, each type of cartilage has a specific role: hyaline for smooth surfaces, elastic for flexibility, and fibrocartilage for handling pressure. Love how specialized our body tissues are.
Totally, Eric. And the best part is how these tissues work in harmony to keep us moving and protected. It's all about structure and function.
So, Dr. Rosario, after all this talk about connective tissues and cartilage holding everything together, it only makes sense to now dive into the ultimate support system of our bodies: our bones. I hear the osteon is the MVP here. What makes it so special?
Oh, absolutely, Eric. The osteon is like the architectural genius of compact bone. Think of it as a tree trunk. You've got these concentric rings called lamellae, and they're organized around a central canal. It's all about efficiency.
Wait, concentric rings? Like actual tree rings?
Exactly. Each ring adds strength and structure to the bone, and then there's the central canal. This is where the magic happens. It houses essential blood vessels, nerves, and veins, keeping the bone alive and functional. Without it, well, the osteon wouldn't stand a chance.
That's incredible. And where do these tiny little channels come into play? Canaliculi, right?
Got it in one, Eric. The canaliculi are the bone's communication system. Picture them as microscopic highways connecting osteocytes, the bone cells, trapped in tiny spaces called lacunae. Through these channels, nutrients, waste, and even signals travel across the osteon, keeping everything coordinated and healthy.
Man, it's like bones have their own city grid, complete with roads and utilities.
Totally. But here's what's even cooler. These osteons are designed to handle stress. Collagen fibers in the lamellae alternate direction with each layer, making the bone resistant to twisting forces. It's a simple yet brilliant strategy.
Okay, hold up. So if I think about athletes or like, I don't know, someone recovering from a stress fracture, how do these structures bounce back?
Great question. Bones are incredibly dynamic. When you stress your bones, like during weightlifting or running, the cells in the osteon sense that strain through the canaliculi network. They communicate and respond by laying down new layers of bone. Over time, this strengthens the bone exactly where the stress occurred. It's like targeted reinforcement.
Wow, our bones are adaptive and proactive. I didn't realize they were, well, alive in such a literal sense.
Oh, they're very much alive. And this dual composition of bones, collagen for flexibility and hydroxyapatite for compressive strength, makes it all possible. It's why your skeleton can take a beating and keep moving while staying lightweight enough for us to walk, run, and jump.
The ultimate balance, strength and flexibility. I'm starting to see why this topic lights you up so much, Dr. Rosario. Dr. Rosario, I'm still blown away by how dynamic and alive our bones really are. So now I'm wondering, how do they actually grow and develop? Endochondral ossification. That's a term I keep hearing. What's the story there?
Eric, this is the big one. Endochondral ossification is like the growth blueprint for most of your skeleton. Essentially, it's how we transition from having soft cartilage frameworks as babies to the solid bones we rely on every day. The process starts with hyaline cartilage. It's kind of like nature's rough draft and begins transforming into bone.
Wait, nature starts us off on a rough draft? I kind of feel a little cheated, but also fascinated. How does the transformation actually begin?
Great question. The first step is what we call the formation of a bone collar. Think of it like putting up scaffolding around a building. You need a framework to start building bone. Osteoblasts, the bone building cells, line up on the cartilage and begin laying down what we call osteoid, which eventually hardens into bone around the diaphysis or center of the cartilage piece.
Okay, so the osteoblasts get to work first. What happens to all the cartilage inside while this is going on?
I was hoping you'd ask. Once the bone collar forms, the cartilage cells inside, chondrocytes, begin getting bigger in size, a process we call hypertrophy. But here's where it gets wild. As they enlarge, they signal the extracellular matrix around them to harden by pulling in calcium. This stiffens the area, but also cuts off their nutrient supply. So,
Wait. So these cells basically doom themselves?
exactly, Eric, those poor chondrocytes, they sacrifice themselves for the greater good, leaving behind an empty but hardened matrix. And this hard matrix becomes the perfect stage for the osteoclasts, our bone destroyers, to swoop in. They clear out the cartilage so the osteoblasts can move in and replace it with spongy bone. It's like tag teaming. One group clears, the other builds.
That's incredible. It's like the ultimate teamwork. Demolish and rebuild. So is this all happening in the middle of the bone?
Exactly. This is what we call primary ossification. It all starts in the diaphysis, the shaft of the bone, but there's also secondary ossification, which happens in the ends of the bones called the epiphyses. Here, the process kicks off a bit later, usually around birth, and instead of forming a hollow medullary cavity like in the diaphysis, the epiphysis stays filled with spongy bone. It's how we end up with strong bone ends lined with cartilage for our joints.
So this is how we get those growth plates everyone talks about?
Bingo. The growth plate or epiphyseal plate is what remains between the diaphysis and the epiphysis while a child is growing. It's a strip of hyaline cartilage that chondrocytes continuously expand and ossify over time, essentially elongating the bone. When someone's growth is complete, the plate ossifies, turning into a solid epiphyseal line.
Okay, so as adults, we don't have growth plates anymore. But bone health and remodeling, those are still relevant, right?
Oh, absolutely. Even though we've stopped growing taller, our bones are constantly remodeling. It's this dynamic process where osteoclasts break down old or damaged bone, kind of like clearing debris, and osteoblasts lay down new bone. It keeps our skeleton strong and lets it adapt, whether it's from changes in stress, injury, or even nutrient availability.
So it's like bones stay in this constant state of renewal. clearing out the weak stuff and reinforcing the strong?
Exactly. And the key player here is communication. Osteocytes, the retired bone cells trapped in lacunae, act like the managers overseeing the whole process. They sense strain or damage and coordinate the osteoblasts and osteoclasts through chemical signals. It's teamwork on a microscopic scale, Eric, and it's absolutely fascinating.
Okay, that's mind-blowing, Dr. R. Seriously, I'll never take my skeleton for granted again. Any closing thoughts to tie this all up?
Just this, our bones are marvels. They're not just static structures. We're talking living, responsive systems designed to support, protect, and adapt. Understanding all these processes gives us a glimpse into how incredible our bodies really are, and that, Eric, is worth geeking out over.
Couldn't agree more. Well, folks, that wraps up today's episode. Until next time, stay curious, stay inspired, and keep learning. Thanks again, Dr. Rosario.
My pleasure. See you all next time.